usual, now we have the first lecture by Yana. So, yes.
Thank you. Now you even can hear me. Okay. So, I recall that we have 5 lectures. At the first lecture we have introduced operator semigroups, evolution equations, and macro processes and relations between them. And today we will have a second lecture. We will discuss a special class of semigroups generated by macro processes, namely failure semigroups, and corresponding macro processes are called failure processes. So, in particular, we establish some properties of the corresponding semigroups, relation of them to integral differential evolution equations, in particular equations with fractional Laplacians or relativistic Hamiltonians, find connections between convolution semigroups of measures in the big processes and continuous negative functions. Okay, so this is the plan for today. So I need Fourier transform, and that's why I just recall what is what, just in case if you don't remember what is the Fourier transform. So we define Fourier transform for nice functions by this formula. So we choose this normalization, so 2p to the power minus d half integral over rd, and we integrate f with the exponents to the power minus I p times q. So this dot means scalar product in rd, because p and q are vectors. So nice functions mean functions from the Schwarz space, that is functions which are infinitely differentiable and decay very fast at infinity with all their derivatives, partial derivatives. Okay, and we define Fourier transform by this formula of this space, and then it turns out that f is a linear bijective continuous operator of this space from Schwarz space into Schwarz space again, and it has continuous inverse. So the inverse Fourier transform is given by the same formula. The only difference is that here we have plus instead of minus. That's all the difference between direct Fourier transform and inverse Fourier transform on the Schwarz space. Again, my slides will be available, so don't worry. Okay, so we can extend this method, the Fourier transform, onto L2. So it will be in this case an isometry from L2 into L2. So the norm will be preserved by the Fourier transform. On the other hand, we can extend the Fourier transform from Schwarz space onto L1, and in this case it will be a bounded linear operator from L1 into C infinity. So this is the estimate of the corresponding norms. Of course, we do not prove all these properties, but just to recall, assuming that we have heard something about the Fourier transform. And some important calculation rules for Fourier transform. So Fourier transform of a convolution of two functions is just the product of Fourier transforms up to a constant, which depends on the choice of normalization of the definition of Fourier transform. So there is a kind of duality between convolution and multiplication, which is preceded by Fourier transform. So Fourier transform produces a duality between convolution operation and multiplication, product operation. So this is the first formula for Fourier of convolution is product of Fourier. And on the other hand, for if our functions are from Schwarz space, then the product also lives in Schwarz space for Fourier transform is well defined. And then Fourier of product is convolution of Fourier transforms of each function. Again, up to a constant, which depends on the choice of normalization. So this is the first duality between convolution and product. There are also two other dualities which are important for us. The first duality is as follows. So the operation of shift. So we have a function f of q. So q is my variable. Now I shift this function, and I can for a vector a, and I consider the shifted function f of q plus a. So the Fourier transform of the shifted function is the same as Fourier transform of the original function multiplied with this factor into the power IA scalar product with it. And again, there is a duality, that is, if we first multiply with a factor, this type of factor, and then we apply Fourier transform, it is the same as we apply Fourier transform to the original function. function and then shift. So again, duality between the operation of shifting the function and multiplication with this factor. And the third duality, which is also very important for us, is the following. So the Fourier transform of a derivative. So Q is a vector variable, so we have partial derivative with respect to, say, k's coordinate of Q. So the Fourier transform of the partial derivative with respect to k's coordinate is the same as the Fourier transform of the original function multiplied with I pk. So P, so Fourier transform maps the variable Q into the variable P. So one should understand it like Q is a variable of configuration space and P is the variable of momentum space. So QP is a phase space. If we differentiate in the momentum, in the space, and then go to momentum space, it is the same as we first go to momentum space and then multiply with the variable in the momentum space. And again, there is a duality, so Fourier derivative is this operation of differentiation is mapped into an operation of multiplication with a variable, and vice versa. If we have first apply the Fourier transform and then differentiate, it is the same as we first multiply with the variable and then apply the Fourier transform. So again, two operations are dual with respect to Fourier transform: differentiation and multiplication with the variable times imaginary unit. Okay, so let us think about this third duality more. In more details, in particular, let us consider the Fourier transform of Laplace operator applied to the nice function f. So Laplace operator is just the sum of partial second-order derivatives. And now we know that Fourier transform is a linear operation. So I didn't say it, but looking at the formula, you see that this operator is a linear operator with respect to f. So since a Fourier transform is linear, we can interchange this sum and Fourier transform, and then we have Fourier transform of the second derivative. So apply this formula twice, theoretically, we obtain that we have to multiply with IPK twice. Okay? So I to the power 2 is minus 1. So this is why we have this minus. And sum of pk squared. So p is the vector, pk are coordinates of this vector. Sum of pk squared is just the norm of p squared. So this notation, like absolute value, this is actually the notation for the norm in RD. So really like a norm, I know the norm of operators or the norm of functions in some function space. But in RD, I use this notation for the norm. So you see, Fourier applied to Laplace operator, Laplace of f, is the same as Fourier of f multiplied with this function of variable. Okay? Agree? Okay, then I apply inverse Fourier transform to both sides of this quantity. So then here, Fourier to the power minus 1 applies to Fourier. They kill each other, so Fouriers disappear, and we have only Laplace. And on the left-hand side, I have function f, then I apply Fourier transform, then I multiply with this function, then I apply the inverse Fourier transform. This is what is written here. So you see, I have a differential operator, which I can represent in this form. So how I apply Laplace operator? I take a function, I apply Fourier transform, I multiply with this function, minus norm of p squared, and then apply the inverse Fourier transform. So this type of operators are called Fourier multipliers or pseudo-differential operators. So here the definition. So let lambda be a function defined on the phase space, so depending on q and p, so both state space variable and momentum space variable, taking complex values. And a linear operator lambda hat defined by the following formula. So how it acts. So this operator, lambda hat, applied to a function phi. And then this is again a function. We consider this function at a point x. And this is defined as follows. We take this function phi, apply Fourier transform, we obtain the function of variable p. Then we multiply with the function lambda of xp. And then we apply inverse Fourier transform with respect to the variable p. And it is again a function, and we consider it at point x. So x here is a kind of parameter. So this is the rigorous formula which we just write explicitly in the Fourier transform. So you see, we have double integral, so we integrate, so to say, with respect to the phase space. So first state space, we take phi, we apply the Fourier transform. This is e to the power I p times minus p. Then we multiply with the symbol, the obtained function of variable p. And then we apply the inverse Fourier transform with respect to the variable p at point x. So this is exactly what is equal to. So this formula defines the so-called pseudo-differential operator with symbol lambda. Of course, domain of definition depends on which Banach space we consider and what kind of function lambda we have. Okay, so lambda is called symbol of the pseudo-differential operator lambda hat. And as you see from the properties of Fourier transform, if my lambda is just polynomial with respect to p, so it depends only on p, and is a polynomial with respect to p, like here, then my pseudo-differential operator is nothing else but differential operator. Like Laplace. In the same way I can obtain any differential operator with constant coefficient. If my lambda is polynomial with respect to p with coefficients which depend on x, then this operator will be just differential operator with variable coefficients depending on x. But if my lambda is not a polynomial with respect to p, exponential function, or sine function, whatever, then this is really a pseudo-differential operator. No more differential, but integral. Pseudo-differential operator. Okay, so you see, so starting from a Fourier transform, we can define a class of operators called pseudo-differential operators. All differential operators are a special case of pseudo-differential operators. Other questions to this definition, to this notion?
So, for example, if I have like this example, so Laplace,
Yes.
so defined for f is twice differentiable.
Yes, so
But
doing
pseudo differential we can define for larger class of functions.
So this is already technical things which we will clarify when we consider particular examples. So in general, everything depends on which lambda and which Banach space we are looking for.
This example we can define for larger class.
Yes. Or at least, so to say, we can define for some, and then we close the operator. What is the end of operator? Sometimes some additional things are needed, but it is for good functions, if you know that the operator is pseudo-differential operator, it is already some knowledge about the operator.
In this, the same way, when the people talk about, for example, the fractional order equation.
Yes.
Or sometimes even consider what's
Yes, it will appear soon to me. Yeah, fractional Laplace was already mentioned that we are going to discuss. And also in the last lecture, it will pop up in the model of anomalous diffusion. So examples. So we will just revise the examples we have seen yesterday. So we always work in these two types of Banach spaces, NP or C infinity. So first example is the heat semigroup. It's a family of integral operators with Gaussian kernel. We have discussed it yesterday. So consider this kernel. Namely, consider the function rho t of x. This is the probability density function of normal distribution, which acts as a density of the kernel in this family of operators. So this function is well known, and we know that its Fourier transform is given by this function, again exponential function, but now again minus norm square of the variable. So here variable is x, here variable is p, but now t, here t was in denominator, and after applying the Fourier transform, t comes to the dominator. So, oops, sorry. So, we'll assume that we know that, or you can calculate it yourself. So what do we see here? So this formula gives us actually a convolution between the function phi and the function rho t. So my semigroup acts as this convolution. This is one. On the other hand, if we consider nice functions phi from the Schwarz space, then what we can do? So tt of phi, so we have already discussed, it is a convolution of phi and rho t. So I just apply this to my, so let me write down in this order, it doesn't matter, convolution is symmetrical. Yeah? Now I use properties of the Fourier transform. The Fourier transform of the convolution is constant times the product of Fourier transforms. So I have Fourier inverse composed with, and I have constant 2 d over 2, and then Fourier transform of rho t times Fourier transform of phi. But I know Fourier transform of rho t. This is this function. So this constant will eat this constant. And in total, what do we obtain? We obtain where my psi is exactly as we have discussed already. Yeah? So agree? So we have just shown that the heat semigroup can be represented as a convolution, and it can be represented as pseudo-differential operator with this symbol. With the symbol e to the power minus t p squared, at least for good phi. But when we have this representation, it's very easy to calculate the generator of the semigroup for good phi, at least for good phi. So if we have a semigroup, the semigroup has this formula. Now I have to calculate the derivative with respect to t of this formula, and at t tends to 0, at t equal to 0. So actually I have to calculate the derivative. So only this part depends on t. Yeah? So I have to calculate the derivative of this guy with respect to t at t equal to 0. And this is nothing else but minus psi. Yeah? So this is again a motivation, but one can show everything rigorously, that it is really so, that for phi from the Schwarz space, the derivative exists and is given by this pseudo-differential operator, but minus psi, so psi has this form, hence this is nothing else but 1/2 Laplacian. So we have, what have we done? We have shown that that for such nice phis, the generator of the heat semigroup is just 1/2 Laplacian. Yesterday I just stated that this is the generator, but now we have even shown, or almost shown, without technical details. But one can check that everything is fine, and hence this set belongs to the domain of generator. So, is it clear what happens? So we just use Fourier transform as a tool to represent semigroups and to calculate their generators. Okay? And it turns out that for many interesting semigroups, they all have the same type. So semigroup has is a pseudo differential operator with such type of symbol, and then the generator is a pseudo differential operator with this symbol. So this is the first example. Let us look some other examples. So multiplication operator, also we discussed yesterday. It also can be represented as pseudo-differential operator with symbol minus c. Now this symbol depends only on x, it does not depend on q. So actually I can pull it out here, and then Fourier inverse and Fourier will eat each other. Symbol does not depend on the momentum theory. And then the multiplication semigroup itself, again, can be represented as pseudo-differential operator with this symbol. Again, this symbol does not depend on b variable, so we can pull everything out here. And this Fourier and inverse Fourier, they eat each other, and we obtain just this. And on the other hand, of course, phi of x can be represented as convolution of function phi and Dirac delta measure. And hence, again, I can represent the semigroup as a kind of convolution. So phi is convolved with some measure, some probability measure, because in the case if the c non-negative, or just some measure. In general case. Okay, one more example. Translation semigroup, also we discussed yesterday. Translation semigroup was defined by this formula, so just a shift. So we take a function and we shift it into the direction b, which is already given in advance, times t, which is the parameter of the operator. Again, this can be understood as a convolution of function phi with Dirac delta measure concentrated at the point tb. Not at 0, but at point tb. So on one hand, we have this convolution representation. On the other hand, again, assuming that phi is a good function, we just, what we can do, we just, should I write it, sorry? So what can we do? We just insert Fourier transform in gross, compose with Fourier here. So let me write it down. So Tt of phi is equal to, for good Fourier inverse composed with phi applies to this function phi at the points. So this is the variable. This is my TB, so this is a shifted function, and now we apply the properties of Fourier transform. The Fourier transform of the shifted function is the same as Fourier transform of the original function times this factor, which we discussed. And then we obtain this representation. This is exactly this factor. Yeah, duality between shift and multiplication with this exponential factor. So applying the properties of Fourier transform, this guy is nothing else but yes?
So you give two examples, actual examples now. One is that lambda is complex value, another is real value.
Yes.
That's the difference between the symmetry of the operator or non-symmetry of the operator. Because this seems like this semigroup is non-symmetrical.
And what?
No, I just wanted to see if this the issue of the complex value or real value will be defined by the non-symmetrical operator operate between the difference between non-symmetry or symmetry of operators, perhaps.
Yes, yes, fully transformed properties of fully transformed. Yeah, yeah.
Okay.
Because if we have a function which is symmetric, it's fully transformed with real values.
Right. So that's okay.
In a sense. Okay. So once again, so we start with translation semigroup. On one hand, we have this convolution representation. On the other hand, using the properties of Fourier transform, at least for root functions phi, we have this representation. That is, the semigroup is a family of pseudo-differential operators whose symbol is again e to the power minus t times some function. And again, on one hand, having this representation, at least for root phis, like Schwarz space, we can calculate the derivative at time t. And again, this is just a pseudo-differential operator whose symbol is the derivative of this symbol at t equal to 0. And this is exactly this expression. Yeah? Okay. But again, recall the properties of Fourier transform, that multiplication with a variable is dual for taking the derivative. Hence, what is written here is nothing else but the first derivative. And this scalar product with B is just the scalar product with B. So we have shown that this operator is a generator of the translation semigroup. We have shown it yesterday, if I'm not wrong. Today we have shown it in a different method using the Fourier transform and its properties. So we have revised the examples we have seen yesterday. And you see that all of them can be considered as examples of semigroups generated by pseudo-differential operators. And you see the symbol here is not a polynomial with respect to P. So it's really pseudo-differential operators. And for heat semigroup as well. Yeah, so the symbol here is exponential function, not a polynomial, and the operator is not differential operator, it is integral operator. Okay, so we have 3 examples of semigroups, operable semigroups, which are given by pseudo-differential operators. And you see that the generators can be found in a very convenient way. We just differentiate the symbol. We obtain the symbol of the generator. Okay, so other questions so far? Okay, then we go further. One more example. The so-called Poisson semigroup. So we fix some vector L in RD and some constant lambda, strictly positive. And we consider the so-called Poisson semigroup on any of our Banach spaces, favorite Banach spaces. So this is the definition. Yeah, and one can check that this series converges. So we really have a bounded linear operator defined on each of these Banach spaces. Okay, so in one hand, again, we can represent it by a convolution. So this is phi convolved with a measure, which is a discrete measure. So a linear combination of Dirac datas concentrated at such points. Yeah, because here we have these points where phi is taken. Yeah, and these factors serve to be sure that the series converges, to simplify it. So this is, on one hand, the convolution representation. On the other hand, so let us first calculate the generator of the semigroup. So again, just recall that the generator is just the derivative of tt at t equal to 0. So if you have this representation, you see that the dependence on t is only here and here. So one can show that you can differentiate each summand, so to say, and consider t equal to 0. You differentiate this series summand by summand, and then consider t equal to 0. So after doing that, you obtain that the derivative at t equal to 0 of this operator is operator L, which has exactly this formula. So only two summands will survive after differentiating with respect to t at t equal to 0. Okay? This is an exercise for you to check. Just working with each summand, differentiating each summand. Okay, so this is so one can easily calculate the generator, and looking at the generator, you see that this is a bounded linear operator in all of these spaces. So this expression is well defined for each element phi of any bounded space X given here. Okay? Further, we again use the properties of the Fourier transform. So I just insert here Fourier inverse composed with Fourier, and then I again use that the duality of shift and differentiation with respect to Fourier transform. Okay? Applying these properties of the Fourier transform, we can represent this expression in this form. So this one is just for this summand. This is Fourier inverse composed with Fourier applied to shift. And this shifted function gives rise to this multiplication with this factor. Okay? So lambda is just multiplication with the constant, it does not control anything. So the generator has this form. It can be calculated explicitly by using the definition of the semigroup, and then using the properties of the Fourier transform. This is nothing else but pseudo-differential operator with this nice symbol. Okay? And as we have said, so this formula shows us that L is a bounded operator. And hence, the semigroup generated by this bounded operator is nothing else but just the function of the operator defined by the Taylor series. Okay. Yes?
So this is very interesting way of extend from R1 to RD. So I guess that's the similar way you can extend this to any semigroup of Markov process, which take, for example, take the values in some linear space, not necessarily Euclidean space. Because you can take that I to be any fixed vectors in that state space.
Yes, yes. The state space should be linear space.
Right. So that's I guess you can use this idea to talk about Fourier transform in non-Euclidean space.
You mean infinite dimension?
Right.
Because linear space is still linear. Yeah,
Right.
I believe it is already done. Okay. So once again, the logic. What's going on? So I have defined this semigroup in this way. This formula allows to calculate the generator explicitly. Just taking derivative with respect to t of each summand and put t equal to 0. So this is the generator. It is a well-defined operator for the whole bounded space. It's a bounded operator. So the semigroup generated by this L is nothing else but this Taylor series. Okay? So if L has this form, then L to the power n can be easily calculated. In one hand. On the other hand, using the properties of the Fourier transform, we have represented this operator as pseudo-differential operator with this symbol. Hence, L to the power n is just, you just iterate this pseudo-differential operator. Yes? So how it works? n to the power n. So we apply to phi. We take phi, we first apply n. This is Fourier multiplied with the symbol and composed with inverse Fourier transform. This is my n. Then once again n. Yes, once again n. What is n? Fourier multiplied with the symbol, and then inverse. Yes? So you see these things will kill each other, and so on and so forth. So finally, what is here is just Fourier inverse composed with minus psi to the power n here applied to phi. Yeah? Hence, and since we have this series, so that is after summing up, I can write it down like this: sum L from 0 to infinity, psi to the power n, multiplied with these factors, t over n, t to the power n over n factorial. But this is nothing else as e to the power minus t psi. So that's why the semigroup is just a differential operator with this symbol. So this is my psi, and the symbol of the semigroup again is minus e to the power minus t psi. So again we have the same story. Okay, so one more. So why I consider this example? Because they are like the basic blocks from which we construct all our examples. So you see, we have seen heat semigroup, translation semigroup, multiplication semigroup, and Poisson semigroup. They all can be represented as semigroups of pseudo-differential operators with symbol of this form for some function psi, and the symbol of the generator is minus psi. This is quite natural. The semigroup itself, the semigroup TT, is an object which replaces e to the power Tn. So, so if L has symbol minus psi, then it's natural to expect that e to the power Ta has symbol minus t psi. And we have seen that examples that it is really the case for this example. Okay, so I recall the definitions which we have discussed yesterday. So operator semigroup is the family of bounded linear operators having these two properties from yesterday. Semigroup is called strongly continuous if we have this condition. So plotwise continuity at t equal to 0. And we define its generator as the derivative at 0, or right-hand side derivative at 0, taken pointwise for such points where it exists. In such points where this limit exists, they form the main definition of the generator. Okay, so now we are finished with the preliminaries, and now we start finally the topic of today's lecture, semigroups and planar processes. Are there some questions for the both?
This scheme of Fourier transform is very much similar to what we call spectral structure.
Yes.
Operation-wise, they're very similar. It's not clear to me is there any direct connections. Of course, the spectral structure is more general because we can talk about spectral structure in any operator, linear or nonlinear space. But they must have something, for example, the property we discussed, a lot of property we discussed for the Fourier transform can work there.
Yes.
I never know that in the literature they directly, talk about, for example, some kind of isometry relation between the Fourier and the spectrum.
Yes,
Like it's where it is.
spectral representation is exactly to go into the dimensional space from the space.
Okay.
So this is, yeah.
Yeah, just like what you just wrote there.
Yeah, but nevertheless, we also generalize something in the sense that so far, all our symbols depend only on one variable, either momentum variable or configuration variable. If they depend on both of them, then everything is not that funny. But we will discuss it soon. Okay, so now let us consider a semigroup. So let Tt be a semigroup of operators on this bounded space, and the point that this is a bounded space of bounded Borel measurable functions from RD. So first definition, the semigroup is called sub-Markov if for any element, any point of our bounded space, semigroup is positivity preserving, namely if it's a non-negative function, then after application of the semigroup we obtain again a non-negative function. And another property is the so-called sub-Markov property, which says that if my phi is bounded above by 1, then my semigroup applied to phi again gives us a function which is bounded above by 1. Okay, so this is the definition of sub-Markovian semigroup. The semigroup is called Markov if it is sub-Markov and conservative. Conservative means that if we apply semigroup to a constant function, this is a constant 1, then we obtain again a constant 1, not something smaller than 1. Okay. So again, the semigroup is defined here, so constant function is a very nice element of this bounded space, bounded non-measurable functions. The semigroup is called Feller if it is sub-Markov. If for any element of the space C infinity, the semigroup applied to this element is again element of C infinity. This is the so-called Feller property. That is, the semigroup keeps this bounded space invariant under extension. And the third property is that restricted to this bounded space C infinity, the semigroup becomes strongly continuous. So this is the Feller semigroup. Sub-Markov semigroup, which keeps C infinity invariant and is strongly continuous on this bounded space C infinity. And recall C infinity is the bounded space of continuous functions vanishing at infinity. Yes, please.
If you have positivity preserving,
Yes.
and you have conservative,
Yes.
then can you obtain automatically sub-Markov property?
I don't think so. No. It's linear. It's a good question. I don't know. But the thing is that we are interested not only in Markovian semigroups but also sub-Markovian. So some of them will not be conservative. So if we have this factor, which will appear once again soon, then if t grows, this decays. So if I apply this semigroup to 1, I obtain something which is not 1 anymore. Now this is the main source of non-Markovity but sub-Markovity. But I don't think so. Okay, so this is the definition of the Feller semigroup. Remark, so if we have a Feller semigroup, or better to say the following. Two remarks. First remark is that the notion of Feller property is defined differently in different groups. But it is always a kind of a property of a semigroup that some space of continuous functions is mapped into some space of continuous functions. But which particular spaces, this is all may be different. Like continuous and bounded functions mapped to continuous and bounded, or C infinity in CD. Yeah, so there are different types of Feller property which give rise to different types of, or different notions of Feller processes, Feller semigroups. But so to say, the most standard one, at least in the research groups where I was working with, it's this one. So as a space of continuous functions, we are interested in, we consider this C infinity. So this is the space which is invariant on the action of the semigroup. So actually, another definition of Feller semigroup will be as follows. It is a semigroup defined on this Banach space, which is a strongly continuous semigroup on this Banach space, and has these two properties: positivity preserving and some Markov property. That is, we do not start here, we start just here, on a smaller Banach space, and that's all. So this is other way around, so to say. But if we start here, so we consider a semigroup on this space, then it turns out that using the Riesz theorem, we call it Riesz theorem, says that the space which is dual to the space of continuous functions is the space of measures. And now there are different forms of this theorem, which clarifies which space of continuous functions and which space of measures should be taken to have this duality. So using the Riesz theorem, it turns out that if we have a semigroup which is defined on C infinity, and which is sub-Markov, that is, it has these two properties, then considering this action and fixing small g and this x, we obtain a linear function on the space of continuous functions, and it has a representation by means of some measure. And positivity preserving allows to choose the measure which is non-negative, and some Markov property allows to choose a measure which is sub-probability measure. And semigroup theory gives us Chekhov-Kolmogorov property, hence we actually show that there exists a sub-Markovian kernel such that my semigroup is nothing else but the a family of integral operators with this kernel, and it is a sub-Markovian kernel. So there are two ways. In one way, we start here and we define the Feller semigroup as it was done before. Otherwise, we start from the semigroup here, Feller semigroup here, and by this theorem, we can extend the semigroup to the whole space, PB. And moreover, it turns out that any Feller semigroup has this form for some sub-Markovian kernel. But as soon as we have sub-Markovian kernel, we have a Markov process on a state space Q or a state space Q plus symmetry. Okay? So if we have a Feller semigroup, there is a process, Markov process. Definition: each time homogeneous Markov process possessing Feller semigroup is called Feller process. What is written here, sub-Markov process, meaning that we have Markov process either on Q, my Q is RD, from now on. So either on the state space RD or in the extended state space RD plus symmetry. So considering this process only on RD, we obtain either Markov or sub-Markov. That is Markov on all the extended space. Okay? So, we have defined a special class of semigroups. They are strongly continuous on this space, the infinity, and they are related to Markov processes. Okay. Example: heat semigroup is a Feller semigroup. We didn't prove that, but one can show it. So the semigroup is generated by Laplacian. But we have seen already that the operators of the semigroup, they are integral operators with this kernel, Gaussian kernel. And this Gaussian kernel is actually some Markovian kernel. It's a transition kernel for a process known as Brownian motion. So Brownian motion is a failure process. Translation semigroup is also failure. So semigroup is generated by this operator B nabla, which is a scalar product with B and nabla. This semigroup is defined as shift semigroup. So we have already seen the representation that the action of the semigroup can be represented as convolution of phi with some delta measure. Hence, we again obtain an integral operator with the kernel, and kernel is given by delta measure. Hence, we again have a submarkovian kernel given by a family of delta measures. Okay, do you still follow me or not yet? Not already. Okay, so what kind of a stochastic process, failure process, is behind the semigroup? This is the so-called deterministic drift. That is, we have a random variable psi 0 and all random variables psi t. And we call that the stochastic process is just a family of random variables. So random variable psi t is obtained by deterministic shift of the original random variable psi 0. Okay? So it's a failure process. One more failure process. Multiplication semigroup is failure if my function with which I multiplicate is non-negative. Again, the semigroup is given in this way. For a non-negative c, this exponent is always not bigger than 1, hence this sub-Markov property can be checked. And again, we have represented the action of the semigroup as a convolution of phi with a measure, and the measure was exactly of this type. So it is again a kind of integral operator with the kernel, and this kernel is given by this delta measure multiplied with this function. It's again a kind of a kernel, sub-Markov kernel. And what kind of a failure process lies behind this semigroup? So the process acts as follows. So looking at the transition probability, you see that the transition from x to some other point is not possible. The probability is 0. So each point stays at where they are. So x is always stays in x, does not move anywhere. But this factor is a killing factor. This shows that the process is like dying out or evaporating. So points are everywhere in the space. They are staying there and they kind of evaporating and vanish. They're evaporating with this exponential rate. So at each point there is its own rate of evaporating. And after the point is evaporated, it comes to the center and stays there. Okay? So this is a stochastic process. Okay. So I recall that in all these three cases we have the semigroups of pseudo-differential operators whose symbols have this form e to the power minus t psi. Psi are different, so for heat semigroup and for translation semigroup, psi depend only on p. For multiplication semigroup, psi depend only on x. So in those cases, psi depend only on one variable. Either the variable of the configuration space or the variable of the phase space. Okay, so I recall the definition of pseudo-differential operator. And now theorem. Cornerstone for failure semigroups. So let Tt be a failure semigroup with some general. So let Tt be a failure semigroup always. So if Tt is a failure semigroup, it is a strongly continuous semigroup on the Banach space C infinity, and hence it has generator. Each strongly continuous semigroup has generator. So this is additional condition. If the space of test functions, that is the space of infinitely continuous functions with compact support, so if the space of test functions belong to the domain of definition of L, that is, domain is rich enough, then L, restricted to this space of test functions, is always a pseudo-differential operator with symbol minus psi. So this symbol, minus psi, depends on both variables x and p, where psi is measurable, locally bounded, and has this long terrible form. So this long terrible form, if you fix x, it will be the famous Levy-Kinchin form. If you know what is it, if you don't know, just forget. I will call it terrible formula. So what is what in this terrible formula? So this psi of xp is the sum of 4 summas. The first summa is C of x. Such summa we have already seen. Second summa is I times vector b of x. So for each x, it is a vector in R D. Scalar product with p. So it's a first order term with respect to p. So C of x non-negative, B of x is a vector. Now A of x is a matrix which is symmetric positive semi-definite. Then A of x times p is a vector, and then scalar product with p. So it's a second order term. And then this, the most terrible term in this terrible formula. So it is integral. Here we have something in brackets. I will clarify what is what when we discuss this formula in many details. So integral over RD minus 0, and we have some measure mu, which depends on x and dy. And it is a measure which lives in this space, RD without 0. And it has this condition. What does it mean? This means that mu does not need to be a bounded measure. It can be unbounded. But this is a nice measure in the neighborhood of infinity. So if we consider a neighborhood of infinity, minimum between these two guys is 1. So 1 mu x dy is integrable around infinity. So mu is bounded around infinity. But mu may have problems around 0. So if z tends to 0, the measure of the z can blow up. But this blow up is controllable by this power of. So when y tends to 0, this minimum is just this y to the power 2. So this is the norm of the vector y to the power 2. And this should be integrable with respect to this measure in the neighborhood of 0. So it's a control of blow up of the measure. So what is what here? So, and first of all, yes, if we have this symbol, then the pseudo-differential operator with this symbol looks as follows. Of course, for good phi, for good functions phi. So here we have just multiplication operator to this term, so probably yeah. So this command corresponds to multiplication operator with symbol minus c. Multiplication with function minus c. Second command, it's a first order term with respect to p. It's a polynomial with respect to p of first order. It corresponds to the first derivative. Yeah, so we have seen this already, this operator. The third operator. So if my matrix A of x would be just identity matrix, then here would be just Laplacian. In general, if my A is just some matrix which is symmetric positive semi-definite, then here we have just trace of matrix A multiplied with Hessian matrix. Hessian matrix is just a matrix of all second order partial derivatives. So this is an operator of second, sum of second order partial derivatives with some variable coefficients connected in this matrix. Okay, and it should be an elliptic operator because of this symmetric positive semi-definite matrix. or degenerate. Okay, so you see these three terms, they build a polynomial with respect to p. And the corresponding pseudo-differential operator with the symbol given by this string summand is just differential operator of second order with variable coefficients, c, b, and a of these. So is it clear with this part, with this simple part? So as soon as we have a Feller semigroup and its domain of generator is rich enough, its generator is always a pseudo-differential operator of a special form. And this form is sum of two parts. The first part, in the sense of symbol, corresponds to polynomial of second order with respect to p with variable coefficients. And hence the generator itself is a second order differential operator with variable coefficients. So it corresponds to the diffusion process, probably degenerate if everything is zero. Okay? And now the most interesting last part. So when we have considered Poisson semigroup, we have seen this symbol. We have seen the operator given by this difference. It was a Poisson semigroup. So let us consider an example, a more detailed example which concerns this part. So example is here. So this is the statement of the Kuresh and von Wandel theorem, and we consider a particular example. So we kill this term. So c is equal to 0, n is equal to 0, and nu is given by a delta measure concentrated at some point a, which is a vector in Rd but not zero vector. Okay? Then nu is a bounded measure. And probably I should start from the following, even before the example, just theorem of correction from von Weidenfels. So why this terrible formula looks so terrible? So why do we need all these terrible things here in brackets? Because we want that our nu satisfies this condition, so it may blow up, and hence so we need all these commands to guarantee that this integral is well defined and something finite. Namely, if we take nice phi, we can use the Taylor expansion of this function around x. Then this will kill the zero order term, and then there will be the first order term and second order term. Okay? Second order term will be fine with respect to the measurement. And the first order term does not need to be fine. And this is a kind of compensation for the first order term in order to obtain something integral. This is roughly speaking the idea why the formula looks so terrible. There are different types of this formula, different forms of this formula, where one chooses different compensations. But it does not matter that's much. Okay, now the example. As a measure nu, I take delta measure concentrated at one particular point, A. Since the measure is bounded, this guy here is nicely integrable. So I can integrate it with respect to y, and I obtain something times gradient phi. So I obtain a summand which has the same form as here, but with some other rule. So I can choose B in such a way that I kill this summand. They compensate each other. This summand and this summand. So this is exactly the choice of B to kill these two things. So I have killed this thing, this thing, this thing, and this thing. So what is left? Only this difference. And if I integrate this difference with respect to this measure, I obtain this operator. But this is the generator of the Poisson semigroup with intensity 1. And I guess it is written here. Yeah, so first of all, of course, the symbol of this guy is just this thing. We have already seen it. and this is the generator of Poisson process with jump size A and intensity 1. Why I have written size with this sign? Because A is not a scalar number, but it is a vector. That is, our process in RD may jump on a vector A. So in the direction of A, in the size norm of A. Okay. So this is the probability that my process take value an. This is given by this way. So we just put an ordinary one-dimensional Poisson process in RD. And it lives in span of vector A, so in one-dimensional subspace of RD spanned by vector A. And it takes values A, 2A, 3A, 4A, and so on, as it is normal for Poisson process. Okay, so I recall that the semigroup looks as in here. So again, intensity is 1, my lambda is equal to 1. And my transition kernel is given. Yeah, so if we have a semigroup, and we know that this is a Feldman semigroup, then of course, what is how to calculate the kernel? So we know that Tt of phi at x is just integral over d phi of y pt x dy. So how to calculate pt x at some set A? This is just Tt applied to the indicator of the set A. Yeah, and of course, this is not an element of C infinity, but it is an element of BB RT. And we said that each Feldman semigroup can be defined here, but can be extended here. Just having this phi to obtain the. So having this t, applying it to this indicator function, we obtain the transition code. Okay. So now one can understand the interpretation of all these factors, C, B, A, and mu. So C is a killing rate, yeah, because we have discussed that the corresponding process, this dying or killing with exponential rate. No movement, just evaporating. B is a drift coefficient because this term corresponds to the deterministic drift. So at each, B depends on x, of course, so at each point we have its own drift coefficient. A is a diffusion coefficient. So again, if the matrix A is just a identity matrix, we have a Laplace operator and has Brownian motion. More generally, we have a diffusion process, and A of x is a diffusion matrix, diffusion coefficient. And then this factor, we have discussed that if my nu is just a delta measure concentrated on point A, then this factor give rise to a Poisson process which makes jumps of size A. So then if I take nu to be a linear combination of delta measures, so it is natural to expect that here we have a kind of mixture of Poisson processes making jumps of different sizes. So each point A corresponds to its particular Poisson process which makes jumps of size A. If I take as a new linear combination of, say, delta at point A and delta at point B, then I obtain kind of a mixture of Poisson processes making jumps A and B. Yeah? So actually all bounded measures can be approximated by linear combinations of delta functions. Yeah? But in general, very roughly speaking, we can understand this term as a term which corresponds to a Okay, uncountable mixture of Poisson processes making all possible jumps, and which jumps are possible, it depends on the support of the measure. Yeah? And also measure defines the intensity of jumps. So this is the interpretation of this measure. So the measure nu at point x is the measure of the second variable. It describes the intensity of jumps from x to x plus 8. If nu does not depend on x, then this measure is known as Levy measure. Okay. So this part is a pure jump part of the process. So the first part is corresponds to a diffusion process with continuous path, and the second part corresponds to a pure jump process which makes only jumps, and which jumps it makes and how often it depends on this measure, the intensity measure. Okay, so this is a kind of something new in relation to what was last week. Last week we discussed on processes with continuous paths. Now, failure processes are not only processes with continuous paths, only jumps, also jumps are included. Okay, now interesting example. Let us consider pseudo-differential operator with this symbol. It is completely non-obvious, but one can show that this sign, so pseudo-differential operator with this symbol, also belongs to this class of operators. It corresponds to the following choice of C, B, A, and B. C is 0, B is 0, A is 0, and only pure jump part is not 0, and the intensity measure is given in this way. So it's given explicitly. So intensity measure does not depend on x. So all coefficients are, so to say, constant coefficients, no dependence on x. And yeah, one can check that in this case we obtain so this operator is a generator of a failure semigroup, and it's a pseudo-differential operator of this form. And of course, not of course, but this operator is called fractional Laplacian because what does mean p to the power alpha? It is p to the power 2 to the power alpha half. And we know that minus p squared corresponds to Laplace operator. So it's a symbol of Laplace operator. So this can be understood as a symbol of minus Laplace operator, and then we take a fractional power of Laplace operator. Okay, so this is the motivation why we call this operator fractional Laplacian, but this is a pseudo-differential operator with this symbol. Of course, for alpha between 0 and 2, this is not a polynomial with respect to p, and this is not a differential operator. It's a true pseudo-differential operator. So the statement is that it is a generator. So this is a symbol of operator which generates a failure semigroup. As there is a corresponding failure process, this failure process is known as symmetric alpha stable Levy process. If you don't know what is it, it does not matter. We don't going to discuss all these properties. This is just like the name of the process. And the transition probability of alpha stable symmetric process is known in closed form only for the case alpha is equal to 1. And in this case, it is given by the so-called Cauchy distribution. You have already seen somewhere Cauchy distribution, so it's a function. Okay, it's a measure with respect to y, dy, with probability density function given by an explicit function, elementary function. Okay, so fractional Laplacian is an important operator, interesting operator. And why it is so important and interesting, so I will in particular clarify at the last lecture. but they just believe that this is an interesting generalization of Laplacian. For alpha equal to 2, we obtain just Laplacian. And there is another interesting operator which is important for application, is the so-called relativistic Hamiltonian. It's an operator which pops up in relativistic physics. And taking into account that p square is a symbol of minus Laplacian, yeah, so we can consider this relativistic operator as a pseudo-differential operator with such a symbol. Again, it is not a polynomial, it's a square root of something. So it's a true pseudo-differential operator. And it turns out that even this psi is also belongs to the class given by this terrible formula, Leibnizian formula. And it also belongs to, so that is this is a symbol, minus psi is a symbol of pseudo-differential operator of this type. And again, C, B, and A are equal to 0 on the pure chance part of the drives. And the measure mu is known, but it is given in terms of some special functions, like Bessel function, integral, whatever. So I do not present the explicit formula for that, but just it is known in the literature and can be found. So the conclusion. There are interesting operators which are not differential, which are pseudo-differential, and still they give rise to failure semigroups and hence failure processes. Failure process is a special type of Markov process. Summary. So what do we have up to now? So if we have a failure semigroup with generator such that its domain is rich enough, then we know how the generator looks like. It has this form. It is a pseudo-differential operator of this form. So it is a sum of differential operator of a second order plus this part is integral differential operator. You have integration, you have differentiation, so this is really integral differential operator. So coming back to the title of the lecture, so this is the integral differential operators which I wanted to discuss. Okay, so if we have a failure semigroup whose generator is rich enough, we know how it looks like. Further, we know that a failure semigroup is a strongly continuous semigroup in this space. Hence, we know already from yesterday that the function which is given by means of the semigroup solves the Cauchy problem for the corresponding evolution equation. So this is integral differential evolution equation. And we solve the Cauchy problem for it in this Banach space. And the solution is known, is given in terms of the corresponding semigroup. On the other hand, failure semigroup corresponds to a Markov process, which is even failure. Failure process is a special case of Markov process. So this process has a transition kernel, Pt is dy, and the semigroup Tt is just the group of a semigroup of integral operators with this kernel. And hence, this Tt, phi of x, is nothing else but the expectation of phi of xt when we start our failure process xt for x. So we have this stochastic representation of this semigroup. So we consider evolution equation, integral differential evolution equation with this operator L. And if it is a generator of a failure semigroup, and test functions belong to the domain of this operator, then the solution of this Cauchy problem exists, is given by this formula, and this is the representation of the solution. Okay? So this is the story of what was discussed yesterday and today, up to now. Now, the theorem of Kuresh and von Weidenfeld told us that if we have a Feller semigroup, so if we start with a Feller semigroup, whose generator is rich enough in this sense, then the generator has this form. Now natural question arises. So if we start from such type of operator, can we guarantee that it generates a Feller semigroup? If we just start with some operator and we know that test functions are in the domain of this operator, so we just take some C, B, A, and U, create an operator having this form, and ask, is there a Feller semigroup corresponding to this operator? In the case of constant coefficients, when my C, B, A, and U do not depend on X, the answer is yes, everything is fine. In the general case, it is not that fine.
So this is maybe she
Yes. So let us first consider the case of constant coefficients. That is, my operator is a pseudo-differential operator with a symbol minus psi, where psi has this form, so no dependence on x. And this is the Levy-Kinchin formula, so classical formula. And in this case of constant coefficients, it is known that the test functions, they actually is a core for my operator L. It is known that the closure of the operator L defined on test functions does generate a Feller semigroup. So the answer is yes. If we start with any operator with such a symbol, with any C, B, A, and mu, but mu should satisfy the condition, which was at the very beginning, then we always have a Feller semigroup. This semigroup, yes, is a family of pseudo-differential operators with symbol e to the minus t psi. Psi is just here. Moreover, it can be represented as a convolution. So the action of the semigroup is actually a convolution with a measure eta t. So we actually have a family of measures eta t. And this family of measures is actually the so-called convolution semigroup of measures. What does it mean? This means that all measures here are sub-probability measures. That is, we have this property. They make a semigroup in the sense of convolution, namely this holds, not a product of measures, but convolution of measures, eta t and eta s, gives us the measure eta t plus s from the same family. And there is an extra continuity condition that measure eta t tends to derive the measure concentrated at 0, when t tends to infinity, tends to 0, sorry, converges in some reasonable sense. It is a bug convergence. It is something which is weaker than weak convergence, but we are not going to discuss all these technical things. The only thing which I would like to mention is that I have also another slides which are called appendix. In these slides I have given all the definitions, like what is convolution, Fourier transform, what is convolution of a function of a measure, what is convolution of measures, etc., convergence of measures, so everything will be available. So if you don't know some definitions, don't worry, just so the slides will be available, and take it easy. Take it as it intuitively should be. Okay, so if we have the special case of a symbol psi with constant coefficients, then everything is fine. That is, the corresponding pseudo-differential operator always generates a Feller semigroup. Its Feller semigroup is a family of pseudo-differential operators with a natural symbol. It is also a semigroup which acts as a convolution with a family of measures which have these nice properties. It's a convolution semigroup of measures. And it corresponds to a so-called Levy process with killing. What does mean corresponds? It means that this eta t, this measures eta t, so which are given here, they give rise to the distributions of random variables. They give rise to distributions of random variables minus xi. What is the small technical thing? Okay? So if you don't know, just in case, Levy process by definition is a stochastically continuous process with stationary and independent increments. In particular, Brownian motion and deterministic drift, they are Levy processes. Okay, but we have here this killing. This is an extra term given by this C. So without C or with C equal to 0, we just have Levy process. With C bigger than 0, we have this extra killing term. So evaporating, yeah, which gives a non-zero probability for the process to die out to go to zero. So once again, so how the things are related. So if we have a process psi, the big process psi, then we can calculate its characteristic exponent, and via this. The characteristic exponent of the process psi is nothing else but just the Fourier transform of the measure eta t, which is in here. And this is already calculated. It is here. Yeah, so once again, you see the same calculation as I have already done. Yeah, so the semi-group is just a convolution. We use Fourier transform to convolution. We apply that. So this I think here should be if it is like this, then it should be e to the power minus t sine. Yeah. Yeah. So you see this is so up to a constant. This is exactly the Fourier transform or the corresponding density of the measure or the measure itself. So the same calculation, so having these two formulas, they say us that the Fourier transform of this measure is just given up to a constant by this exponent. So we have this. And yes, the Levy process is a Markov process, and its Markov kernel is again given in terms of this convolution semigroup, which measures eta t, just like this. Again, because once again, so the corresponding sub-Markov kernel is just given by this theory. In one hand, on the other hand, we have this representation. Yeah, so TT is a family of integral operators acting like this. And that's why we can calculate what is P. P is given in terms of this eta and change of variables. Okay. Taking into account your phases, probably I have to write it down in a explicit way. So TT phi of x is phi convolved with eta t. So this is integral over Rd. Phi of x minus y, eta t dy. And now I have to make a change of variables. Okay, let me make it z here, dz. And now I want to make a change of variables. This is my y, roughly speaking. And then what is my dz? Well, I assume that it will be x minus dy. If I'm not wrong. Very Russian, yeah? Just to motivate why we have this. Okay. What does this mean? This means that my TG is the translation invariant semigroup. That is, if we have a function, we apply the semigroup and then shift everything. It is the same as we first shift the function and then apply it to semigroup. On the other hand, this means, on the language of processors, that well, I have no place to. I have to print something. So if I have a Levy process which starts at 0, probably it was this. Okay, so it starts at 0. It's my Levy process which starts at 0. So this is fine. How to obtain the process which starts not at 0, it's on x? Just shift everything to minus x, shift my coordinate system to minus x. And then, so if I forget the original coordinate system, and consider this coordinate system, then this process in this new coordinate system will be just a process which starts at x. That is 3x which starts at x, the process psi which starts at x, is nothing else but x plus process, the same process which starts at 0. So we just shift all of the paths. So I have shifted the coordinate system because I don't want to write down the paths once again. Just take the process, run it from 0, and then if you shift all the whole picture somewhere into x, you obtain the process which starts in x. And hence, in particular, this property means that, so we know that Tt phi of x has this representation. So here the process starts in x. So I can rewrite it as follows. Its expectation which start of the so here we start at 0, and here I use this process. So the same process, the same Levy process with the same transition Markov problem, but now it starts at 0. So x from here is moved here. We start at 0 and move everything into 2x. Why I write it down, because in the next slides you will see sometimes this representation for solutions of the equation. Sometimes you see something like this. That's why, at least for Levy processes, it is the same. Okay. So general case. Yeah, so now everything will be just without calculations, without just another view. So general case, when psi and the symbol does depend on two variables, x and p, nothing is so nice as before. Namely, there exist many different types of sufficient conditions on psi implying existence of a Taylor semigroup with the corresponding generator. It is given in different terms, in terms of martingales, in terms of SDEs, etc. But they are very different and they cannot be unified. There are counterexamples. That is, some psi's given by this awful formula, terrible formula, they are not generators. They do not correspond to generators of Taylor semigroups. Moreover, we don't know how these operators look like. This doesn't work anymore. So so once again, so what do we have? I have operator L, which is a pseudo-differential operator with symbol minus psi. Assume that it does generate a Taylor semigroup. And psi depends on x and p. Then Tt exists. Semigroup exists, but it is not of this form. Moreover, the operator which stays here doesn't have a semigroup property. So we don't know. So even if we obtain the existence result for the semigroup, we don't know how it looks like. Nevertheless, we know that still this is the family of pseudo-differential operators with some symbol. But the symbol is not as we had before. So, if
So when you say that's a counterexample, you mean the counterexample that's this
for some particular size,
say even not even if correspond to any semigroup, not necessarily failure, right? So failure means a semigroup with some continuity.
well,
so what's
counterexamples which I meant, they were about the processes, so failure semigroups, semigroups generated by some processes.
So you mean, okay, so forget about the failure property. So if you have lots of kind of representation for that side, does that correspond to any, any semigroup, not necessarily failure?
No, not necessarily. As I said, this guy is not a semigroup.
Okay.
That's why probably it does.
So the continuity is not the issue here. So.
Yeah, it's so what's it?
So this the problem is not about the continuity, right?
No. But nevertheless, if the coefficients explode too fast, then there is a problem. Okay, so as soon as we have a symbol which depends on two variables, even if the symbol is given by the variable formula, we cannot guarantee that there exists a corresponding failure symbol, so hence a corresponding stochastic process. One thing. Another thing, even if we can guarantee that the process exists, we don't know how the semigroup looks like. It does not look like as before. I mean, this is not a symbol of the semigroup. Semigroup is still given by pseudo-differential operators with some symbol, but it is not this exponential function. However, if our coefficients A, B, C, and mu are good enough, continuous and bounded, the only one thing which we can state is that the derivative of the symbol with respect to t at t equal to 0 is still minus psi, as it was before for this function. So as soon as psi depends on only one variable, x or p, everything is fine. As soon as it depends on both variables, everything breaks down. So how to fight with it, we will discuss at lecture number 4. So of course, if there is a semigroup, but we don't know how it looks like, then we have to approximate it. Yeah, so something is still doable, but it will be the lecture number 4. So the natural question arises how to construct, approximate, and represent a strongly continuous semigroup, in particular failure semigroup, in this general case, where even if the failure semigroup exists, we know only this. Okay, so this is this leads to the lecture number 3, where we will discuss classical and less classical methods for construction, approximation, and representation of a semigroup. And here I have a list of literature, which are just textbooks, which are fundamental textbooks for those who are interested in the theory of semigroups and the theory of Markov processes and pseudo-differential operators, Levy processes in particular. Okay, that's all. Okay, thank you. So, are there any questions? Yes.
So obviously that's a failure semigroup is very important subject.
Yes.
But on the other hand, I was thinking about this. Most in the practical situations, normally the semigroup is given by a Markovian or sub-Markovian curve. So then you have a choice to make that semigroup on different space. For example, L in L2. Okay,
Yeah,
I will point out L2. But the reason I point out particularly L2 is because L2 have a nicer structure For example, in L2 space, your Fourier transform can have isometry.
Yes.
You know, that's a lot of computation can be carried out in L2.
There are Dirichlet forms, there are many tools.
Right, right. So I just wonder why the literature does not concentrate a little bit more on that's the semigroup on L2 instead of.
Because well, L2 theory is very nice for symmetric fields.
Yeah.
And this is not always
Yeah.
the situation. So it's wonderful that we have a Hilbert space and a self-adjoint mechanism. And everything is so fine, everything works, we have a spectral field, we have everything.
You can compute.
Yes. But the life is more complicated. In particular, I assume that when it is plutonium, I'm not sure if it is self-adjoint.
Okay.
Probably, even yes, but sometimes we need very good efficiency. Yeah.
No other questions? Any comments? Okay, you will get the slides, and maybe if you read it once more, maybe you will have other questions, so you can ask anytime. So, thank you. And now we have a break until 2 p.m. So,
See you later.
yes, you can go. Lunch.